Okay, good afternoon. So we are continuing with the GARCH models. So we have learned the arch models, and now we are trying to define what is called a GARCH model. So what is this GARCH model is? So the setup remains the same. By that what I mean is you have the RT and then RT equal to mu t plus epsilon t, and mu t is of course the conditional mean, which I'm not writing now, and then you are trying to model epsilon t equal to sigma t z t. This is also same where z t is IID 0 1. Now, what is here the difference is that the specification in the case of arch is sigma t square is alpha naught plus alpha 1 epsilon t minus 1 square plus etc. plus alpha m epsilon t minus m square. So this is something like similar to AR kind of model. It's not exactly AR because AR will have a error term here. This doesn't have an error term. So this is AR is stochastic. This is deterministic. Why deterministic? At the time point t, all these are known to me. So it's a deterministic. Now in the case of GARCH, what we are going to do is that uh, apart from these errors, at the time point t, the volatility which happened on the previous day is also going to affect the volatility on today. So that will be much more reasonable. So I will have a model like this: sigma t square is equal to alpha naught plus summation I equal to 1 to m alpha I epsilon t minus I square plus summation j equal to 1 to r beta j sigma t minus j square. So this is called a GARCH MR. So this is something similar to the ARMA kind of model. So what the additional thing is, if all these beta j's are 0, this is going back to your arch. So this is called generalized arch. Okay. So this is what we are going to discuss today. So essentially everything is same, the setup is same. Only thing is that the volatility equation that we are using is being changed now. It is changed from this to this, because earlier I had only this, but now I'm changing to this. So I'll get a GARCH model. And of course, so let's see that. So the GARCH model is basically introduced by Robert Engel, Rob Engel's students, a doctoral student. And ARCH model was introduced by Rob Engel. I have shown you the photo of these three guys. In fact, Engel and Boleslav. So Boleslav is a student of Rob Engel. Rob Engel got the Nobel Prize for this arch-GARCH invention. Boleslav developed the generalized arch model, abbreviated as GARCH, in 1986. And as I mentioned, it is defined like this. And of course, there will be restriction to the parameters for the finiteness and non-negativity of conditional variance. Now, the parameters are restricted, like this is strictly greater than 0, and this is greater than or equal to 0. This is also greater than or equal to 0. There will be an additional condition comes, because if you want to talk about the variances, therefore I equal to 1 to maximum of MR, alpha I plus beta, actually this should be beta I, alpha I plus beta I less than 1. So this should be read as beta I because I have only I here. So alpha I plus beta I less than, otherwise I should write j equal to 1 to MR, alpha j plus beta j less than 1. So the last condition guarantees that the unconditional variance is finite, because yeah, this we will we'll show you that how this is in the coming discussion. So basically this has something to do with the unconditional variance. You remember in the case of AR model, you have 1 upon 1 minus phi sigma square upon 1 minus phi square, and then you want that phi to be lying between -1 to +1, so that phi square is less than 1. So something similar happens in this particular case as well. That's the reason this condition comes. So as I told you, you get into higher and higher moments, the condition will be more and more stringent. It will not be say, simply like this. This is just to start with. So you can leave at this point, but then I'm not sure whether the variance exists, what will be the variance, what will be the fourth moments, etc., etc. So in order to have such things, we need to have better stringent conditions every time. So existence of higher order moments may demand more stringent conditions on the range of parameters. So let's, like you remember that I have defined an eta t and then written the arch in the form of a MA model. So in a similar kind of thing, we can write GARCH in the kind of as a ARMA type model. So that's not difficult. I'll just show you that with this. So it's like I'll take this equation and then I'll write. So this equation is I'll just sigma t square. I'll subtract sigma t square and add epsilon t square. Okay. So I have to do the same thing here. Alpha naught plus. So I have to subtract sigma t square and add epsilon t square over here. So what will happen is that this will be epsilon t square is equal to all this stuff plus eta t, where eta t is epsilon t square minus sigma t square. Okay, so you can see that now that what will happen is that because there is some change will appear. This the reason being that you can look at this here. Uh, this coefficient remain the same. So you have, you see, you have because I have, I can write sigma t square in terms of. See, the substitution here is sigma t square or epsilon t square minus sigma t square equal to eta t. So I have to now, if I write sigma t square in terms of these two, so it will be epsilon t square minus eta t. This will be sigma t square. So I'm going to do that substitution over here. So what happens that you have this kind of, this is like a original variable and this is kind of innovations. You will be writing this and the coefficient which appear over here, this will be adjusted with this also, and this coefficient stand as a separate for this, and there will be an error coming over here, and that leads to this kind of an equation: epsilon t square equal to alpha naught plus I equal to 1 to p. Remember that in such a case this cannot go for both r and m, so it will go to the maximum of whichever is the maximum, it goes up to that. And of course if I mean, like, we may have to take some convention, like, so those betas will be 0 if this is maximum. From here, that point onwards, m plus 1, m plus 2, m plus 3, m plus r, I mean, those will be taken. I mean, you may have to take these betas to be 0, something like that. You may have, so that's the reason that the maximum of mr comes here. It goes up to that. And now if you look at this very carefully, so this is kind of resemblance related, I mean, having a resemblance like ARMA kind of structure. So for example, if this is observations past values, and this is like errors, and this errors past, and this is the current error. So this is exactly like a kind of ARMA type representation. So it is possible that this equation can be represented in this way by defining eta t as epsilon t square minus sigma t square. I think I have written that epsilon t square minus sigma t square as eta t, and then you substitute. I've given you the enough hint so that now you are in a position to complete this. The only difference is that in the case of ARMA, when we define, these are like white noise, but now this is actually white noise, mean 0, uncorrelated, but we call this as martingale differences. So this is eta t is a martingale difference, which is like mean 0 and uncorrelated. This is uncorrelated for j greater than or equal to 1. So it is not IID in the case of ARMA, because ARMA we say that this is normal means this will be IID, but that's not the case over here. Now, in this case, it is possible to see that now this has mean 0. That's very simple, because if you take eta t, expected value of epsilon t square, then you make condition on that past value. So this will remain as such, and this will turn out to be sigma t square. So sigma t square minus sigma t square is 0. So this has mean 0. That's how you get the mean 0. And you can find the covariance and then show that it is also equal to 0. So you can see that expected value of epsilon t square is equal to alpha naught into 1 minus this quantity to the power of minus 1. So now you can realize that why I want this fellow to be less than 1, because if this fellow is greater than 1, then this will be negative, which is not acceptable to us. So I want this to be less than 1. So that's why this condition, this condition is coming over here. Sorry. So this is what it can be seen that the square expectation of epsilon t square is this quantity. How did I get this? That can be computed here, because its expectation means it is alpha naught. This will be there plus same quantity over here. So you take this on the other side, and then alpha naught upon 1 minus of this, because this is, I am assuming, a stationarity, and these expectations are 0. So I am assuming a stationarity, you can directly get this expression. If it is not stationary, so that's what I told you, that we are, in all these computations, we are sort of making an assumption that this is stationary. So if it is, you can't do the other without that. Then question is that who told you that it is stationary? Well, that needs to be justified. So we have a section on that, but I am sort of keeping that kind of, there is a little involved. So we don't actually prove those results. We'll state them so that you know what is the stationarity that you're talking about, what is the condition that is required, etc. Okay, so proofs are not included, only statements are included. So here I am assuming that epsilon t square is stationary, epsilon t square and epsilon t minus I square has the same expectations. So therefore the expectation turns out to be this. Okay. Now generally, now you may think that this is more complex because I have p terms here and r, m terms here and r terms here. It's pretty difficult to handle this. Actually, in practical sense, in real practical applications, these m and r will be 1 or 2, something like that, 1, 0, 2. I mean, generally it doesn't exceed beyond 2. But of course, it doesn't matter even if it exceed. Nowadays, computer is doing the business. But most of the cases, I think 1, 2, etc. will be sufficient. So GARCH 1, 1, GARCH 2, 1. 1, 2. Many situation 1, 1 model will be adequate. Now for the estimation, what we do is that we assume, like in the earlier case, I have to assume, you see this is the model, I have to assume a distribution for this. And using that distribution, I'll be able to write down the likelihood and then get the maximum likelihood estimators. Provided what may require is that the complexity, like in the earlier case also, here say for example, you may require the starting values, because the starting values can create a problem, because when you are at time 1, this is 1 minus, so this is 0, depending on the order, you need 0, you need minus 1, you need minus 2, etc. up to 1 minus m. So you need, or in general, if it is like similarly for this also. So if I assume m is larger, so you need those many terms which are there. But we don't have observations for those terms because we start from 1 only, epsilon 1 square. You don't have epsilon 0, you don't have epsilon minus 1, epsilon minus 2, which is like basically 1 minus m. So you may have to go m step backwards. So what we'll do is that these are called the initial values, and we have seen that in the case of ARCH, we make some assumption about the initial value. Something similar is also need to be done in this context. But the problem here, there it was enough to consider epsilon squares, but here we have to consider epsilon square as well as sigma square because these also appear on the similar line. So we need to make such assumptions for both of this if you want to write down the likelihood, etc. Or even in the prediction also the same thing. So, what we are saying here, for the estimation conditional maximum likelihood method can be applied provided the starting values of these are known. For example, for a GARCH 1 model, we need to have sigma 1 square to be treated as fixed, then sigma 2 square can be computed recursively using GARCH 1 equation. Because there is a sigma 0 square will come when t equal to 1. And what is sigma 0 square? Of course, this is like 1 and 2. You can also have 0 and 1, etc. So the sample variance epsilon t, now sometimes what happened that we sort of assume that for those values, anyway, we don't have information. We assume that they are either same with some value or they are equal. I mean, they are 0. There is no variation if they remain the same. We make an assumption so that we can start writing it. So this sample variance serve as a good starting value of sigma 1 square. So the fit of the model is checked using the standardized residual. This is exactly same as what we have seen earlier because how the model will be fit, if your fit for sigma t is correct, then the epsilon t by sigma t, all the assumptions of zt will be satisfied. So that is how we just justify the fit. Okay, so let's look. So that's what you look at the absolute or square residual of the ZT hat and then decide whether the correlations have been taken care or not, or variances have been taken care or not. That means running through the time, the heteroscedasticity has been taken care or not. That's what you see. Okay. Now let's look at some of the special cases. GARCH 1.1. The simplest case is GARCH 1.1. And in the GARCH 1.1, so the model turns out to be this. I put m equal to 1 and r equal to 1. So you get this equation, GARCH 1.1 equation. Now the parameter restrictions the corresponding to this. So this is the parameter restrictions. So I have alpha 1, I have beta 1 and alpha 1 plus beta 1 less than 1. M and R are 1. So maximum is also 1. So alpha 1 plus beta 1 less than 1. So that's a restriction that I get. So the parameter restrictions are there. Now here also we can show that kurtosis is this is greater than 3. This calculation is slightly involved, but it's not difficult. You can actually write this equation. So how do you start with this calculation? You use this definition, epsilon t, and then use the, so I'll just give you a hint and maybe you can complete it yourself. So what we want is epsilon t to the power of 4 variance of epsilon t square. So I want to compute square. This is what the kurtosis is. So epsilon t equal to sigma t zt and sigma t square equal to alpha naught plus alpha 1 epsilon t minus 1 square plus beta 1 sigma t minus 1 square. This is my equation. So if I want to, when I compute epsilon t to the power of 4, what I will do, expected value of sigma t to the power of 4 zt to the power of 4. And this actually is simplified as sigma t is function of the past values. So I'll write this as a conditional on this. Sigma t to the power of 4 zt to the power of 4 given ft minus 1 and then take one more expectations over here. Okay, so that's called the smoothing property of the conditional expectation. And this sigma t is function of this, so it comes outside this expectation. So sigma t to the power of 4. Oh, wait a minute. Yeah, epsilon t is equal to sigma t z. This to the power of 4 means this to the power of 4. And then I have zt to the power of 4 given ft minus 1. Now, this is anyway condition or non-condition is not going to make any change because this doesn't depend on that. So the for assuming zt to be IID normal 0 1, we get this is 3 times of that. So we have to have expectation of z to the power of 4 is 3 sigma t to the power of 4. Now here I may write this as 3 times expectation of sigma t square and then square. Okay. Now you can simplify this by substituting the value of sigma t. So what I get here is sigma t square as alpha naught plus alpha 1 epsilon t minus 1 square plus beta 1 sigma t minus 1 square. Okay, so this is sigma t square and I have square. Okay, now what you can do, you use the similar trick over here, and you may have to use some notations for this, because I may have to cancel out or bring it on the same side and then simplify this whole stuff, and that I'm stopping at this point. You can continue with this. So that leads to an equation like this. Of course, you have to divide by this quantity, which I have not done because I was computing only this quantity. So together, it leads to an equation like this. And again, because this is less than 1, you can see that this is greater than 3. This entire thing is, greater than 1. So you will see that this is greater than 3, which means that it has still heavy tail. The kurtosis is more. Now, if you see this, you see that this is a simulated series, and this is simulated with this omega stands for alpha naught, and this is for alpha 1, and this is beta 1, and normal distribution is taken. You can see that this volatility is happening over here in this particular case. So now, how will you estimate this model? So these are the observations, n observations from this, and I'm writing sigma t as this root of ht. So it's like ht as sigma t square. So sigma t is root of ht. Okay, that's just a notation change. So I'll write it like this. I assume that zt is IID 0, 1, and ht is this equation. Same, I mean, there is no change. Only thing is that instead of sigma t, I have used this ht notation here. That's all. And what are the parameters? The parameters are alpha naught and alpha 1, alpha 2, alpha m, beta 1, beta 2, beta r. And you can see that these can be 0 to infinity, and this can be strictly greater than 0. So you get the parameter set is something like this. And what we'll do is that, as I told you, for estimation, we need the initial values, because when you are starting at a point 1, because of the recursive equation, you need to go back. So I assume that these are the initial values: epsilon naught square, epsilon minus 1 square, etc., epsilon 1 minus m square, and sigma naught square curl. This curl, actually I am putting it because I am just assuming that these are initial values, so it is subjective. Like, people can take it as simply as 0, or you take the marginal variance and substitute it for all these fellows, or some things like that. So there are various ways to handle this initial values. So in order to write down the likelihood, we need to specify the distribution of ZTs, because if you want to write down the likelihood, we need to specify the distribution of ZT, because ZT is epsilon t by square root of HT. So, for example, so I'm going to discuss two types of things, like, because this is a scale family. I told you that because you are attacking the variance, the model is a multiplicative model or a scale model, because you cannot add something so that the variance change. So you can only multiply, the variance get change. So I have, because epsilon t equal to sigma t zt, so zt is epsilon t by sigma t. Therefore, when I write the distribution of zt is f, I can say that the likelihood is given by 1 by sigma t f of epsilon t by sigma t, where sigma t square is to be recursively computed using this equation. So this is a scale family. The maximum likelihood of theta n, theta is this m plus r plus 1 dimension parameters. So I will be able to find the maximum likelihood estimator from there. obtaining by maximizing the likelihood. This can't be done manually. So it is possible to establish the consistency and asymptotic normality of the MLE theta in hat with some assumptions. I give you a reference of Franken's coin. Actually, I think I have put this on the sharing thing. So you have Frank and Coin's book where they talked about asymptotic normality, consistency and asymptotic normality. Anyway, it is not a part of our syllabus, but those who are interested, they can actually look into that. So the maximum likelihood estimator is consistent and asymptotically normal. How do I write the likelihood is written, and this I have to replace with the appropriate assumption. If I am taking normal, then I have to do that t with that, etc., etc. So this is how the estimation is done. And similarly, you can also write the quasi-maximum likelihood, because sometimes what happens that we are not sure what kind of distribution this ZTA has. So what I do, if it is, instead of assuming a particular one, I assume that it has some particular form, and that form is that of the normal. And then whatever the distribution, irrespective of whatever it is, I assume that it is like this. And this is called quasi-maximum likelihood. So L theta is the quasi-maximum, the likelihood is this, and then you maximize this. So the QML is defined as the argument maximum of this function with respect to the theta. So you have to maximization problem with a m plus r plus 1 dimension maximization problem, because this function is of dimension. Not only that, you have a recursive equation in that, because sigma t square you have to assume it has to be obtained recursively. So this is what the estimation process is all about. Now there are some suggestions here. The unconditional variance is reasonable to choice. Reasonable choice for the unconditional variance is you assume that all these are equal to the marginal variance. So this is the marginal variance. And anyway, you have estimated these values, substitute them. But there the problem may come that you may get this to be negative, because you are substituting alpha 1 hat and beta j hat, sorry, alpha j hat, alpha I hat and beta j hat for this equation. It can happen that because these are estimates, this could be negative. So in such a case, you may have to have a constraint estimator, like if it is negative, take the estimator as 0, otherwise whatever the value that you get. Alternatively, we may consider whatever the epsilon 1 square, the first epsilon 1 square, because that is an observable quantity. You can take all of them equal to that and then proceed with epsilon 2, epsilon 3, etc. So all these are this, and now just start doing this. So it is possible to establish again the consistency and the asymptotic normality. So the QML is a quasi-maximum likelihood where we assume that irrespective of whatever distribution, you assume a normal kind of structure it has got. Whereas in the maximum likelihood, you write the appropriate one. So that's why we did not write even. What is that? Okay, because depending on the assumption of this f, we have to write down. Whereas in the quasi-maximum likelihood, we always say that it is of this type. Now computer does this maximization, so we don't have to worry too much. Now come the last aspect, what is called the volatility forecasting. So volatility forecasting is done like forecasting in the ARMA model. So for example, if you consider one step ahead sigma t square, so sigma t plus 1 square is alpha naught plus alpha 1 plus beta 1 sigma t square plus alpha 1 sigma t square and zt square minus 1. This zt square minus 1, because I have, this is like you remember that we have done this exercise. This is eta t, so I'll be replacing it with that corresponding thing. So you will get this kind of a thing in this context, and if you take the expectation, so that's what the first step, one step ahead forecast. So what will be that? Alpha naught plus alpha 1 epsilon t square, because I'll be replacing this epsilon t square plus beta 1 sigma t square. Where do you get alpha 1 epsilon t square? This is because one step ahead forecast of this is, sorry, see, something that cancels here, sigma t square, alpha 1. So you get, this is like ARMA forecasting, exactly like that. So you get, this is if you have the values sigma t square done earlier at the time point t, we can substitute it here and get the sigma t plus 1 square. So that's what it is. I have replaced it with sigma t square over here. This can be obtained from here, beta 1 sigma t square. The expectation of this is 0, so that is why alpha 1 sigma t square. Sigma t square, I mean like I am actually going to replace it with epsilon cheese. So this is what epsilon t square plus beta 1 sigma t square, just to maintain the the format. That's all. I mean like because that will help us when you go for sigma t plus 2. Now t plus 2, you can see that that will be alpha naught plus alpha 1 plus beta 1 sigma t plus 1 plus alpha 1 sigma t plus 1 square is zt plus 1 square minus 1. So this is the equation that you get. Again, doing the same stuff here. This I will be replacing it with this fellow, and if you simplify, that leads to this kind of an equation: alpha naught plus alpha 1 plus beta 1 into sigma t square 1. That means this is the volatility estimate of the first t plus 1, and this is t plus 2 now, etc. Continuing in this, so you can see that in general this reduces to this kind of an equation: alpha naught into 1 minus alpha 1 plus beta 1 to the power of L minus at the L step. This is for the second step. One step, two step, etc. L step, you get this plus this quantity. And then if you allow L to go to infinity with an assumption alpha 1 plus beta 1 less than 1, you can see that this is actually alpha naught upon 1 minus alpha 1 plus beta 1. And as L tends to infinity, this goes to 0. This entire thing goes to 0, which means that the conditional variance, this is basically the volatility, the conditional variance, that actually goes to the marginal variance. See, uh, this is possible because I have made this assumption. So you can see that this forecast, so slowly when you start forecasting the volatility, and if you are trying to forecast it for very large n, you will be forecasting it by the marginal variance. But for smaller n, smaller L, not n, smaller L, you will have different values, which are, see here I don't have the alpha naught upon 1 minus alpha 1 plus beta 1. It is different. Whereas here also I don't have. So as an L become larger and larger, it converges to this. So this is what the volatility forecasting is all about. And compare the out of sample volatility forecast with the squared. This you can actually compare them to see how good they are, and because this is within that. Now you will, when you reach at that time point, you can get these things. So you can have a comparison of this. You can see that there will be low correlation between these two, uh, I, because you are now, there may not be a very high correlation, because you will have correlation between epsilon t when you are here. When you are here, there will be very high correlation between t plus 1 and sigma t plus 1 square. But when you go far, I mean in terms of this, this correlation, low correlation coefficient between this epsilon t plus L square is alone not adequate measure of volatility at the time t plus L. So you may think that, okay, why not just take this? That's where the significance of the GARCH comes, because if epsilon t plus 1 square is the only things, then actually this is not irrelevant. This is going to be irrelevant. So it is not that, because for volatility, what is happening is that whatever the error happened, it is okay, but there is something also in between, something more happens, so that volatility gets accumulates. So that your sigma t square today is not just epsilon t minus 1 square what has happened on the previous day, but something more will happen, and that's what uh, this whole thing tells. So we know that this is equal to this. This is a consistent estimate of this, but it is not an accurate, because this is just a single observation estimator of the variance. Okay. Now, GARCH model also has a similar kind of problem that we faced in the case of ARCH model. And again, GARCH model is just a simple manipulation of ARCH model. It doesn't address many issues like asymmetry and other things are still not being addressed. So people go for asymmetric volatility models, or there are different types of asymmetric volatility model. One of the student did PhD with me on that asymmetric volatility model, who is now a police commissioner. and special Naxalite cell at Nagpur. Yeah. Okay. So that's about this. So we'll stop at this point of time.